So, welcome to the first CRM-PIMS-AARMS invited lecture at the Joint Math Meetings. My name is Jaidev Atreya. I'm the Co-Director International for the Pacific Institute for the Mathematical Sciences, or PIMS. PIMS, CRM, and AARMS are predominantly Canadian mathematics institutes, and we've come together to sponsor this lecture to highlight the deep connections between Canadian and American mathematics. With me on stage is Galia Daphne from CRM. We didn't have, AARMS is the Atlantic Association for Research in the Mathematical Sciences, and that's very far away in Atlantic Canada. So Sanjeev Sera, the director of AARMS, sends his regards. Octave Cornea from CRM sends his regards, and Oscar Yilmaz and Christine Bauer, other parts of the leadership from PIMS, also send their regards. These institutes exist to create collaborative networks in mathematics. You may have visited CRM in Montreal, or you've been at a PIMS event. We encourage you to learn more about our institutes, and hopefully this lecture will be the first of many wonderful lectures highlighting the exciting mathematics that's happening. With that, I'll turn it over to Galia briefly, who's going to tell you about a nice event that's going to happen right after this. So let me pass it on to Galia.
Thank you. Welcome, and I want to invite you all to a coffee break sponsored by the CRM-PIMS-AARMS partnership, which will take place in the exhibit area at 11 a.m. following this talk. So you're all invited. And I want to invite now Leah Benish, who is a professor at University of North Texas, and she will be introducing today's speaker.
Good morning. I'm honored to introduce someone who very likely doesn't need any introduction. Henri Darmon is a distinguished James McGill professor in the Department of Mathematics and Statistics at McGill University. He received his bachelor's degree from McGill University in 1987 and PhD from Harvard in 1991 under Benedict Gross. After a postdoc at Princeton with mentor Andrew Wiles, he joined the faculty at McGill in 1994. Henri works in algebraic number theory, in particular elliptic curves, modular forms, and L functions. His work is motivated by Hilbert's 12th problem and the Birchon-Swinnerton-Dyer conjecture. To name just a few of his career achievements, Henri has been awarded the Royal Society of Canada's John L. Synge Award, the André Azinstadt Prize, the Coxeter-James Prize of the Canadian Mathematical Society, the Riebenboim Prize of the Canadian Number Theory Association, the CRM Fields PIMS Prize, and the 2017 AMS Cole Prize in Number Theory. He was elected to the Royal Society of Canada in 2003. Henri has also been awarded the Leo Yaffe Award for Excellence in Teaching at McGill University. Indeed, he has been referred to as God's gift to math students at McGill on Rate My Professor. He also provides exemplar service to academia by serving on 7 editorial boards, including Transactions of the American Mathematical Society. Henri has advised over 30 PhD students and mentored approximately 50 postdocs. He seems to be an endless source of energy and creativity and is incredibly generous with his ideas and with his time. Everyone likes to talk to him about their projects because even when the topic is only remotely related to their to his research, he appreciates the subject and enthusiastically makes insightful comments and suggestions. Above all, Henri is incredibly kind. I think I'm not making any unrealistic assumptions when I say he is universally well-liked. Today, he will tell us about Fourier coefficients of modular forms. Please welcome Henri Darmon.
So thank you, Leah, for this very kind introduction. So the topic of my lecture today is going to be modular forms and their importance in various parts of mathematics with a strong emphasis on number theory, and especially various applications to number theory questions that arise through the Fourier expansions of modular forms. So I'm going to begin by sort of a general thing. I mean, so of course, number theory is about numbers, and the integers are the most basic of those. They're as old as human thought, perhaps older. I mean, that's a bit of a theological question, but it was Kronecker who said that God created the integers and all else is the work of man. And indeed, number theory is also concerned with the various number systems that one can build out of the integers, like the rationals, which one gets by looking at the field of functions, the field of rational, I mean, of fraction field of the integers, then the algebraic closure, the field of algebraic numbers, and then things that you can obtain by extending the number system by adjoining various fundamental constants of mathematics, like pi and e, for example. And then the complex numbers, say, which you obtain by a process of completion, which is a field which is good for doing both algebra, since C is algebraically closed, and analysis, since it's complete. And we'll see towards the end of the lecture that other completions of the rational numbers can play an important role, most importantly the p-adic completions, which we'll talk about a little bit towards the end. Now, mathematical functions are arranged in a sort of analogous hierarchy. Most basic among them are the so-called polynomial or rational functions, where those are simply the functions that can be built up from the four basic operations of algebra: addition, subtraction, multiplication, and division. And then there are the trigonometric functions, which you all learned about in high school. And then just beyond that are the modular functions, which are the main theme of this talk. And this talk is going to be devoted to special aspects of these modular functions. They're pervasive, I think, in all of mathematics, in large parts of mathematics, and I want to focus on their importance in number theory. So what is a modular function? It's simply a holomorphic function on the basic domain of definition is the so-called Poincaré upper half plane, the set of complex numbers with strictly positive imaginary part. And one looks at functions that satisfy the two basic symmetries, that they're invariant under translation and under the transformation which sends z to -1 over z. Now, these two transformations together, and one also requires that the function satisfy some kind of reasonable growth condition as the imaginary part of z goes to infinity, or as z goes to the boundary of the upper half plane. And these translation and the inversion together generate an infinite group, the group of Mobius transformations with integer coefficients. So one simply requires indeed that the function be invariant under all elements in this SL2Z, 2x2 matrices with integer coefficients. And here's a well-known picture of the so-called fundamental domain for the action of this group, SL2Z, on the upper half plane. Every element of the upper half plane, every complex number with positive imaginary part, can be translated by essentially a unique element of SL2Z so that it lands in this region, with this shaded region which I've drawn here. It's kind of a strip of width 1 lying above the unit circle. So in other words, a modular function is determined by its values on this fundamental region. Okay, so a modular function in particular, therefore, is periodic of period 1. It's invariant under translation, and because of this periodicity, it has a Fourier expansion. It can be written as some kind of in function of the basic function e to the 2 pi I z. And the reasonable growth condition that I alluded to in the earlier slide translates into the property that the expansion that f admits an action expansion as a nice Laurent series in Q, this variable Q, which is just e to the 2 pi I z. And this is a standard notation to call Q e to 2 pi I z, and one often talks about the Q expansions, therefore, of modular functions when one talks about their Fourier expansions. So these complex numbers that arise in the Fourier expansion are called, of course, the Fourier coefficients of f, of this form, of this function. And the Fourier expansions of modular functions and mild generalizations, which I'll talk about a little bit more later, called modular forms, provide generating series for a surprisingly rich variety of mathematically interesting sequences that arise naturally in mathematics or that arise in various branches like algebra, number theory, and mathematical physics. Okay, so I'm going to begin with perhaps the most important basic example, the so-called J function, which was intensely studied in the 19th century by mathematicians like Klein and Fricke. It turns out that all modular functions are polynomials in this basic function, the J function. So it's the unique modular function whose Fourier expansion starts off like this. Starts off as 1 over q plus 744. That constant is a little bit arbitrary. I mean, it's just an additive constant. But so there's a unique modular function which starts off like that. And the further coefficients in the Fourier expansion are these. And what you already notice, one reason why that object is of interest in number theory is that these coefficients are actually integers. And they're not random integers. They have a lot of interesting structure. So for example, John Mackay famously observed that 196884 is 1 plus 196883, which might not seem so remarkable, except for the fact that 196883 arises in a completely different branch of mathematics, in the representation theory of finite simple groups. There's a well-known classification of finite simple groups, and there's this famous largest non-trivial sporadic simple group called the monster. And 196883 is the dimension, the smallest dimension of a non-trivial irreducible representation of this monster group. So there's this completely unexpected connection that arises between representations of finite groups and these modular functions. And this has led to an entire field known as monstrous moonshine. And it's still very active today. There's in fact an AMS session at this meeting here devoted to mock modular forms physics and applications, which is organized by Amanda Folsom, which is devoted, one of the important themes of that session is this theory of monstrous moonshine. So I'm going to now talk a little about a slight generalization of modular functions, the so-called modular forms, which are simply homomorphic functions satisfying a slightly more general symmetry under the Mobius transformation. So instead of asking that the function be invariant under such transformations, one allows a simple automorphy factor, so this factor cz plus d to the k, which you see here, to intervene in the transformation formula for the modular form. And that one asks that, of course, for all matrices at SL2Z, but one also allows possibly subgroups, and one relaxes the symmetry requirements by allowing proper subgroups. The most important one for the purpose of my talk are the matrices in SL2Z, which are upper triangular modulo an integer n. And this n is sometimes called, this is called the level of the modular form. And then also it's customary to require a slightly stronger growth condition at infinity. One requires that the Fourier expansion be a Taylor series and not just a Laurent series, so that there be no negative terms in the Laurent series expansion. Okay. Now the integer k that appears in this automorphy factor that I have up here is called the weight of the modular form, and n, this integer that arises in the subgroup, is called the level. Okay. And a very important feature of the theory is that the space mk of n, the space of modular forms of weight k and level n, is a finite dimensional vector space. It's finite dimensional. And that's going to be important because we're going to see that various generating series arise that lie in the space of modular forms. And then if we can find some independent basis of the space of modular forms, and then just do the linear algebra, one often recovers interesting and highly non-trivial identities for the arithmetic sequences that we're trying to understand. Okay, so one example of this is the partition function. So the partition function represents the number of ways that an integer n can be expressed as a sum of positive integers without regard to the ordering of the integers in the sum. And this function is a very important one. It figures prominently in the work of Ramanujan and many other mathematicians afterwards. And if we look, so if you want to understand this series, it has a rather rapid rate of growth as n goes to infinity. If you want to understand the series, it's natural to try to package it into the sequence. It's natural to package it into a generating series, sum of p of n, q to the n, like this. And if you add 1 to this series and raise it to the power minus 24 and multiply it by q, you get a well-known function, the so-called Ramanujan delta function, which turns out to be a modular form of weight 12 and level 1. So it's sort of one of the first non-trivial examples of a modular form. And so there's this connection between its coefficients and those of the partition function, and that can lead to many sort of insights into, for example, the rate of growth, asymptotic formulas for p of n, and even closed formulae for it. And this kind of topic, this kind of application is certainly covered in another AMS special session at this JMM meeting on partition theory and Q series, which is organized by William Keith. Okay, so yeah, so anyway, this connection, as I said, leads to interesting insights about the growth rates of the partition function. Okay, so the importance of modularity. So Eichler remarked that there are 5 fundamental operations in mathematics: addition, subtraction, multiplication, division, and modular forms. It's a bit of a, I don't know if it's an apocryphal quote, but the general principle which I want to convey in this lecture is that realizing a sequence inside as Fourier coefficients of a modular form can lead to important results about it, to important insights. And I want to illustrate this point with 4 key examples. So the first is a famous theorem of Lagrange on sums of 4 squares. The second is Weyl's proof of Fermat's theorem. The third example is a remarkable result of Gros and Zagier, which concerned with the values, special values of modular functions, like the J function, at imaginary quadratic arguments. And the fourth is an extension of this to real quadratic fields. So of course, given that I'm going to talk about these 4 topics, certainly the first 3 are major important results in number theory. I'm necessarily going to give a bit of a shallow treatment of these topics. But what I want to convey is a sort of a profound unity in the approaches that lead to the proofs of these results, which are all based on studying the Fourier coefficients of certain modular forms and using in a crucial way the principle that in small weights and levels, these spaces of modular forms are often trivial, and that leads then to very interesting and non-trivial results. So I'm going to begin with this first example. The basic point here is that representation numbers of quadratic forms appear as Fourier coefficients of modular forms. So if I let B be some positive definite bilinear form, so simply a function which is linear in each variable from z to the k, on z to the k, on a lattice of rank k, then I can consider the counting function rb of n, which counts the number of vectors in z to the k whose length, whose square length, is equal to n. Okay, so that's a nice arithmetic function which we'd like to understand. And the basic result, which gives us a handle on this kind of sequence, is that the generating series, sum of rb of n q to the n, is a modular form of weight k over 2. So we even know the weight very precisely, and on some subgroup of SL2Z, which depends on the discriminant, essentially, of the quadratic form. And the proof of this result, the proof that this this theta b satisfies the requisite transformation properties, is based on the Poisson summation formula. Okay, so now I come to Lagrange's 4 squares theorem. It asserts that every positive integer is a sum of 4 squares. So for example, 1 is 1 squared plus 0 squared plus 0 squared plus 0 squared, etc. And so every integer that you can think of, you can always write it as a sum of 4 squares. Okay, so if I write R4 of n to be this function, Rb of n, where b is this special quadratic form, where b of the vector is just the sum of the squares of the coordinates, so the standard dot product on z to the 4, if you want, then, okay, so the proof proceeds as follows. This theta series, this generating series for R4 of n, which I've written out here, turns out to be a modular form of weight 2 and level 4. So it belongs to the space M2 of 4. And independently of that, we know that this space is actually two-dimensional, and it has an explicit basis given by the theory of Eisenstein series. And these Eisenstein series have also Q expansions, but the Fourier coefficients in those are ostensibly quite different. They're given in terms of simple modifications of the divisor function. So this sigma j of n, which is at the bottom of this slide, is simply the function which takes the sum of the divisors of n that are relatively, or that are not divisible by j. Okay, so it's a simple modification of the divisor function. And so you have the generating series for sigma 2 and sigma 4 of n, which are modular forms of this weight 2 and level 4. And so already from this, by pure thought, we know that the function R4 of n, which we would like to understand, is going to be some simple linear combination of this divisor function. So we're going to get some nice concrete formula for it in this way. And so you can just do the linear algebra, but here it's even easier because a simple observation, you realize that theta 4 of q is equal to that second Eisenstein series, the one at the bottom there, whose coefficients are sigma 4 of n. And so that allows us to complete our proof. The main principle is that theta 4 of q is a linear combination of these two Eisenstein series. And in fact, theta 4 of q is this 1 plus 8 sum of sigma 4 of n q to the n. And now we can just have to equate the coefficients in this expansion. And we find that R4 of n is the 8 times the sum of the divisors of n, which are not divisible by 4. And that's immediately shows, of course, that R4 of n is non-zero, since there's always a divisor of n which is not divisible by 4, namely 1. Okay, and that's a positive sum of positive integers, and therefore is non-zero. And so that, in particular, we conclude that R4 of n is non-zero, giving Lagrange's theorem. Okay, so that's a very classical sort of application, a sort of very much 19th century application of these ideas. I mean, this was not Lagrange's proof, in fact. It's sort of really, it came later and based on the theory of modular functions, modular forms. So the second example is elliptic curves. So elliptic curves are also going to give rise to interesting arithmetic generating series. So if I have an elliptic curve, simply an equation of the form y squared equals a cubic in x, where a and b, these rational numbers, are to be viewed as the parameters of the equation. Well, one thing we can do, so there's always associated to such an elliptic curve an integer, which is this so-called arithmetic conductor, which is not, it's not important the exact definition, but it measures the amount of bad reduction, the amount of singularities that the curve acquires when you reduce it modulo a prime. So in particular, only for the primes dividing n does the elliptic curve not reduce modulo p to a non-singular equation. Okay, so it has singular reduction at those primes. So for all the primes that do not divide this conductor, we can reduce mod p and we get a nice elliptic curve over the field of p elements. And the most basic invariant of that is the number of points that it has over z mod p. So you can just count the solutions. And then there's this fundamental quantity, ap of e, which is just the difference between the number of points on e over fp and the naive count, which would be something like p plus 1, if you just and then you can extend that function to all integers, first to prime powers by this kind of slightly complicated looking recursive formula for ap to the n of e in terms of the lower powers of p. And you can then extend it to all integers by requiring that the function should be multiplicative, so that an1, n2 should be just an1 times an2 when the two integers n1 and n2 are relatively prime to each other. And that determines the function on all integers. And the important thing, though, is really this thing that I've put in the square box, that this sequence really encodes information about the mod p reductions of the elliptic curve as the p varies over all the primes. Okay, now the big result about this, so now we can form a generating series, sum of a n of eq to the n. The big result is that this generating series is a modular form of weight 2 and level n. That was known as the Shimura-Taniyama conjecture, and it's the theorem that was proved by Wiles around 1994. And Wiles has a truly marvelous proof of this result, but it's too long, unfortunately, to fit on this slide. So I'll just move on. But what I do want to say is some words about how this led to Weil's proof of Fermat's last theorem. That's actually more germane to the theme of my lecture now. So Fermat's last theorem, as you all know, is the statement that this equation, x to the p plus y to the p equals z to the p, has no, what did I say here? It has no integer solutions with x, y, z equals 0, okay, when the exponent is strictly greater than 2. And so if A, B, C is such, the proof is the following. If A, B, C is a solution, we can form a special elliptic curve. Y squared equals x times x minus a to the p, x plus b to the p. And this gives rise to a modular sequence. We can look at the a and the v's corresponding to that elliptic curve. And Weil's theorem tells us that that sequence is the generating series for that sequence is a modular form of weight 2 and some level. This level is rather large. It's the product of all the primes that divide the putative solution A, B, and C. But this elliptic curve has a special property, which is that its discriminant is essentially a pth power. And that's essentially equivalent because the discriminant is going to be something like a to the p, b to the p times a to the p plus b to the p, which is c to the p. So it's a pth power. And that actually has an incidence on the nature of the modular form. Namely, if you look at these integer coefficients, this integer sequence, and you reduce it modulo p, then it turns out, and that was a key insight that came before Weil's proof. It originated with Frey, and then was developed further by Serre and Maser, and finally by Ribet, who proved that this sequence, if it corresponds to a modular form of that large level, has to be congruent modulo p to a modular sequence of weight 2 and level 2. But then, here's the punchline, there are no modular forms of weight 2 and level 2. It turns out that the finite dimensional space is actually trivial, and therefore we get Fermat's last theorem. So the punchline is that because of the non-existence of modular forms in a certain space, Fermat's last theorem has to follow. Okay, so now I get to my third example, the theorem of Gros-Zagier about what are called singular moduli. So a singular modulus is simply a value of the J function at a quadratic imaginary argument, so an element of the upper half plane which satisfies a quadratic equation with integer coefficients and necessarily negative discriminant since it lies in the upper half plane. It can't be on the real axis. So if I look at a quadratic imaginary field, it's a field generated over Q by the square root of a negative integer, then there's a theorem that dates back at least to the work of Gauss, Kronecker, and so, that for all tau which are in this imaginary quadratic field K and in H, the special value of that J function, that basic modular function I introduced earlier, is an algebraic number, and it generates an abelian extension of that quadratic imaginary field. And these values are quite fascinating. They're important for many things. For example, the explicit construction of class fields, abelian extensions of the quadratic imaginary field. Historically, they were an important motivating example for class field theory, which is one of the big developments in number theory, the first half of the 20th century and 19th century. And so these numbers have a lot of interesting structure. One of them lies in their factorizations. So if you try to factor this function, j of tau, it turns out that, firstly, that if the ring of integers of the quadratic imaginary field is a unique factorization domain, then the value of j of tau is actually not just algebraic, it's even a rational number, and in fact, it's even an integer. And so we can look at these integers and look at how they factor. And so here I've written down the various values of tau for which the corresponding imaginary quadratic field is a unique factorization domain, has a string of integers with unique factorization property. And in each case, what we observe is that these integers are clearly not random. They're highly factorizable. They're products of small primes with large multiplicities. And this also arises when we look at the differences of singular moduli. So for example, if I look at j of tau minus 1728, this 1728 is not chosen at random. It's the value of j at I, so it's itself a singular value. And then these differences also have interesting, highly composite factorizations with no small prime factors. So this is remarkable because a typical integer, if you take one at random and you factor it, you tend to have a large prime divisor, at least of size the square root of the integer you started with. So it's kind of, these are highly atypical factorizations, so it's clear that some structure underlies the behavior of these numbers. And this was systematized, so I mean, it was really, people already in the 19th century were aware of these patterns, but I think the first very general result was obtained by Gros-Zagier much later in the 1980s. And the theorem is that if you take two tau1 and tau2, I'm going to assume that their discriminants are fundamental, so they're actually the discriminants of a real quadratic, of the ring of integers of an imaginary quadratic field, and that they're co-prime to each other. So if I take tau1 and tau2 like that, I can look at the difference, j of tau1 minus j of tau2, this natural invariant. And moreover, and what we're going to do more precisely is, okay, so I let hi be the field, generated by j of tau I over the field ki. So for I equals 1 to 2, I have these two abelian extensions of the various imaginary quadratic fields. And the theorem of Gros-Zagier says that the norm of this algebraic number, down to q, is an integer which has a completely explicit factorization. And it tells you all kinds of things about the prime factors that appear in this factorization, in this product. So the first is that all the L's that appear should divide a positive integer which is of the form d1, d2 minus a square over 4. In particular, those primes are all less than the product d1, d2. So that gives a strong upper bound on the primes that arise in this factorization. And these discriminants are also always either 0 or non-quadratic residues modulo each of the primes that appears in this factorization. So there's a lot of structure which is proved, and in fact the theorem of Gros-Zagier is even more precise than that. It even gives, for each of these L's, each of these suspects, it gives an explicit formula for the multiplicity M sub L with which they appear in the factorization. So there's really a very general, a very precise result here. We really understand very well how these quantities factor. Okay, so I want to say now a few words about how that proof proceeds. So the proof of the Gros-Zagier theorem is simply to consider the expression of interest, or rather its logarithm, the logarithm of the absolute value of this norm, and subtract the sum of the M sub L's times the log of L's, where L ranges over all these small primes less than d1, d2. And what they show in their proof is that this rather complicated looking quantity is actually the first Fourier coefficient of a modular form of weight 2 and level 1. And again, for the same reason that Fermat's last theorem is true, that there are no modular forms of weight 2 and level 1, for that same reason, that modular form has to be 0, and therefore this coefficient A1 has to be 0. And so out of that you get the theorem of Gros and Zagier on the factorizations of differences of singular moduli. So this is a rather remarkable, again, application of the same principle. Okay, so that's how we recover this result. Okay, so this idea of understanding factorizations of differences of singular moduli by trying to see them in the Fourier coefficients of modular forms turns out to be useful in various more or less conjectural generalizations. So one important question that's certainly motivating me over the last decades is whether one can try to extend this kind of formalism, this theory of singular moduli, to settings where the imaginary quadratic field is replaced by a real quadratic field. So if d1 and d2 now are positive discriminants, and we look at tau1, tau2 to be these kind of quantities, then we would like to try to make sense of something that would play the role of j of tau1 and j of tau2 and their difference. So we'd like a function of two variables, j of tau1, tau2, that behaves like the difference. But the key difficulty that arises, of course, is that the elements tau1 and tau2 are not on the upper half plane anymore. They're kind of degenerated to the boundary, and the function j has essential singularities at the boundary, so you can't make sense of evaluating. But what you get as a kind of consolation, as a structure for these real quadratic irrationalities, is that if you have a tau 1, you can look at its algebraic conjugate, which I call tau 1 prime. That's another point on the boundary of the upper half plane, and you can draw a geodesic. I mean, this upper half plane is a natural hyperbolic structure, hyperbolic metric. SL2Z acts as hyperbolic isometries on this space. And the geodesics joining tau 1 and tau 1 prime is a natural object, a natural geometric object. So we can do that for tau 1 and tau 2, and we get some kind of invariant, a very poor topological invariant, which just reflects the intersections of these two geodesics, whether they intersect or not. Okay, so that's going to lead us to, so our proposal for a generalization of difference of singular moduli is going to be based on this topological invariant in the following way. So I'm going to let tau goes to tau prime be the natural involution, which sends a square root to its negative. And I let this gamma j be the geodesics that I wrote down on the previous slides, the one that joins tau j to its algebraic conjugate tau j prime. And I define the topological intersection to be exactly what you think it is. It's either 0, 1, or -1. The sign of the intersection depends on a choice of orientation convention. I choose the right hand or left hand rule, whatever. I mean, whatever you prefer, and that gives you a systematic notion of intersection sign, I mean, of signed intersection. So now we're going to define a kind of local intersection between two real quadratic numbers, tau 1 and tau 2. To first order, I mean, it's just basically the difference of tau 1 and tau 2. We're trying to make some interesting quantity that involves the difference of these two numbers. But then we multiply it by its conjugate, tau 1 prime times tau 1 prime, and then normalize this product, this norm of the difference, by taking tau 1 minus tau 1 prime and tau 2 minus tau 2 prime, which is essentially the square root of d1 and the square root of d2. They're just a normalizing factor. But the important thing about this expression you see here is that it's a simple cross ratio of tau 1, tau 2, and its two algebraic conjugates. And this, because of the Galois symmetries inherent in this expression, it actually belongs to the quadratic field obtained by drawing the square root of d1, d2. And the important further thing is that I raise this cross ratio to the power of the topological intersection between gamma 1 and gamma 2. So if, in particular, if the two geodesics do not intersect, my g of tau 1, tau 2 is just going to be 1. And I will only get something interesting when the two geodesics intersect. And it'll be either that expression to the power 1 or -1, depending on the sign in which they intersect. Okay, so this, by its very nature, you can easily see that it's a point pair invariant. It's invariant under translations, in fact, by any element of SL2R, in fact, or SL2Q. If you simultaneously translate tau 1 and tau 2 by some matrix in SL2Q, you will not change the value of this function g. But we want to make something a bit more global. We want to make it invariant under SL2Z in a more serious way. We want to make that the function of two variables is invariant under substitutions for each of the variables. So I'm going to let gamma be SL2Z. It acts on the real quadratic elements by Mobius transformations, clearly. And it acts also on the space M2 of Z of 2 by 2 matrices of integer coefficients by left and right multiplication. And so I'm going to let gamma 1 and gamma 2 be the stabilizers of these two real quadratic elements, tau 1 and tau 2, respectively, for this Mobius action of SL2Z. Okay, so now what I'm going to do is I take the product over all the matrices of a certain determinant, let's say determinant M, of g of tau 1 times the translate of g evaluated at tau 1 and the translate of tau 2 by this matrix alpha. And it turns out that because of this condition, because I put this intersection number, this product, it turns out to be a finite product. So I'm only taking a product over the double cosets. If I multiply alpha on the left by anything in gamma 1 or on the right by anything in gamma 2, it's easy to see that the resulting expression g of tau 1 alpha tau 2 will be invariant, will be unchanged. So we want to overcount these things infinitely many times. But when you've taken this product over this double coset space set, you get a finite product. So because it's a finite product of algebraic numbers, it's itself an algebraic number, it belongs to this quadratic field, q square root d1, d2. And this, so that's what I'm saying here in the slide below. Okay. And therefore, and also, because I've sort of taken this product over SL2Z for the second argument, and I started with a function that was a point pair invariant, this function gm of tau 1, tau 2 does satisfy the suggestive modularity property that if I translate tau 1 and tau 2 by different elements of SL2Z, the resulting value will be unchanged. So it's really invariant under SL2Z cross SL2Z. Okay, well now I want to do some analysis. If I want to get some interesting numbers that are not just in this quadratic field and some abelian extension, I need to take some kind of limiting process, like in the case with the modular functions, you would take some kind of complex limit. Now the big difference here is that the difference will be taken in a p-adic sense, which is something which is comes very naturally to number theorists. So we define a distance on the rational numbers by decreeing that two rational numbers are very close to each other if their difference is divisible by a high power of a fixed prime p, okay, in the numerator, of course. And that's a distance which is very natural if you're interested in questions about congruences, modulo prime power. You can think of a solution to a Diophantine equation, modulo p to the n, as an approximate solution to a solution in this field of p-adic numbers, in this completion. Okay, so I fix a prime p, and the important thing is that this prime, the two discriminants, d1 and d2, should be non-squares modulo p. So the Legendre symbols, d1 over p and d2 over p, should be -1. And that implies, on the other hand, that the other quadratic field obtained by joining the square root of d1, d2, that d1, d2 is going to be a square modulo p. Okay, so that third Legendre symbol is going to be 1. Okay, so while these quadratic elements do not lie in the upper half plane, that was the whole problem, that they generate to the boundary, they do belong to a kind of p-adic avatar of this upper half plane, which is simply obtained by taking the complement in CP. So CP is the natural thing you would do if you wanted to generalize the complex numbers to this situation. So QP is a completion of Q. It's analogous to the real numbers. The algebraic closure is a field which is nice for doing algebra. So QP bar is nice for doing algebra because it's algebraically closed, but it's not complete anymore. And that has to do with the fact that QP bar is of infinite degree over QP. So it's not so good for doing analysis. But then if you take a further completion, you get a field which is both complete and algebraically closed and contains QP. And that's a field we call CP, and it's a bit more complicated to describe than C, but it plays an analogous role in this theory. So we now take the complement of QP in the CP. In the case of the upper half plane, we took the things with, that sort of broke up the complex plane into two pieces, and we took the upper region. Here, there's no natural upper and lower, so we just take the whole thing. And that symmetric space is called the Drinfeld p-adic upper half, even though the word upper is not really so appropriate. Anyway, it doesn't really matter that much, but so this is what it is. And what we're going to do is, so we have these functions, these quantities g of tau 1, tau 2, and capital GM tau 1, tau 2, which are p-adic. Now I think of them as p-adic numbers rather than real numbers, and I can do that because d1, d2 is a square modulo p. And what I do then is I'm going to be interested in taking some limits. And what I do is I take the limit of g sub p to the n as n goes to infinity. And that quantity I'm going to call j sub p tau 1, tau 2. Okay. And we would like to understand these limits if they exist. It's not at all clear from the way I've defined them that these limits exist a priori. Okay, so the first result, the last I think I'm going to state, is that so if p is one of these primes, 2, 3, 5, 7, or 13, then, so this is a theorem that we proved about a year ago with Jan Vonk, my collaborator. So the p-adic limit, jp tau 1, tau 2, this limit of gp to the n, is a p-adic number, exists in QP, and moreover, it's actually an algebraic number. It belongs to the compositum of two class fields, or in this case, the two Hilbert class fields of the real quadratic fields associated with tau 1 and tau 2. Up to a possible torsion ambiguity. And furthermore, this quantity exhibits the same factorization patterns as the differences of singular moduli, j of tau 1 minus j of tau 2, in the theory of Gross and Zagier. Right, so in the case when tau 1 and tau 2 were imaginary rather than real, we had this thing, and we have very much the same factorization behaviors. So the only primes that arise are less than the product of the two discriminants. They divide an integer of the form d1, d2 minus t squared over, etc. So there's all kinds of, so for example, its prime factors always divide a positive integer of the form d1, d2 minus the square over 4p. Okay, so how does the proof proceed? The proof is actually very much modeled on the original proof of Gross and Zagier, this analytic proof based on the Fourier coefficients of modular form. So the key result we prove is that there's some algebraic number in the compositum of these two class fields for which, if you look at the log of this analytic quantity jp tau 1 tau 2 that I produced before, and you subtract the logarithm of this algebraic number, the result is the first Fourier coefficient of a modular form of weight 2 and level p. And then the punchline is that, well, so we call that in the theorem, we had assumed that p was one of these 5 primes. And what's special about them is that there are no modular forms of weight 2 and level p for those primes. So p is small enough here that there are no modular forms. And so, for the same reason as for Gross-Zagier, we obtain the algebraicity and factorizations of this quantity jp tau 1 tau 2. So it's a kind of first stab at trying to understand explicit class field theory, which was kind of carried out in the sphere of complex multiplication for other settings, for other ground fields like real quadratic fields. And the crucial principle here is really this idea that the Fourier coefficients of modular forms are rich enough to be able to generate these interesting algebraic numbers that belong to abelian extensions of real quadratic fields. Okay. So I'm going to now summarize my talk. So the point I wanted to bring across is that the Fourier coefficients of modular forms encode many interesting quantities that we would like to understand. So the first example was representation numbers of quadratic forms, number of ways which an integer can be written as the value of some quadratic form. The second are the mod p point counts for elliptic curves. You have an elliptic curve, you want to understand how the number of points mod p are linked together as p varies, as the prime p varies. The third example was these differences of singular moduli, the values of the j function at imaginary quadratic arguments. And the fourth were these kind of candidate that Jan Vonk and I proposed for differences of singular moduli in the setting of real quadratic fields. Okay? In all cases, the basic principle was that the non-existence of modular forms of small weight and level leads to important consequences once you've realized these quantities that you're interested in as the Fourier coefficients of suitable modular forms, that the generating series are these modular forms. So in the case of representation numbers, we obtained Lagrange's 4 squares theorem, that every integer is a sum of 4 squares. In the case of mod p point counts, we obtained Fermat's last theorem. That was one of the exciting applications of Weil's proof of the modularity of this sequence. For differences with singular moduli, we recovered this, well, by now I guess classical 1980s theorem of Gross-Zagier on the factorizations of differences of singular moduli. And finally, a similar approach led to the algebraicity of this kind of p-adic variant that works for real quadratic arguments that I proposed with Vonk. Okay, so that was really what I wanted to say. So I'll stop here and thank you for your attention.
Are there any questions?
Yes.
So when the prime is not 2, 3, 5, 13, do we still have the A1 and Fourier coefficient of the modular?
Yes, absolutely. That theorem is very general, so I'm going to kind of go back to that. So this theorem here makes no assumption about the prime. It's only in the application, indeed. I want to conclude that A1 is 0 to get a theorem. But knowing that, so you can define also variance. You can define, you can take the limits of a sub m p to the n for various m's, and that's going to be the mth Fourier coefficient of the same modular form. And so then for primes that are not one of these small ones, the space of modular forms arises as an obstruction to this theorem, here being the algebraicity of these quantities being true on the nose. And indeed, we know that these quantities in general are probably transcendental for larger p. However, this obstruction is finite dimensional. And we have infinitely many identities. And so if we take any combination that annihilates the space of obstructing modular forms, we do get algebraicity results for general p. It's just that these results are a bit more complicated. So here, I mean, I emphasize this one because it's sort of similar to the punchlines that you see in the Gros-Zagier and Fermat, et cetera. But yes?
In your last diagram, you have like a nice result you get. What
Yeah.
is kind of the next research? And like, what's the next kind of result you're trying to show?
Ha. You mean in this vein of exploiting the triviality of spaces of modular forms to get, I mean, there are many other examples, and I mean, this was already a bit of a tall order to talk about these, three big results at the beginning. So I kind of, I was necessarily rather superficial in my treatment, but there were even other examples that I was tempted to include. There's one which is a very beautiful ongoing work of Akshay Venkatesh and Mathilde Gerbeli-Gauthier, which gives a new proof of the Fourier interpolation theorem of Wiazowska, where they somehow relate, I mean, somehow again, the punchline of their proof is that modular forms of weight 2 on SL2Z arise as an obstruction to the truth of this theorem, and because there are no modular forms, so there's a nice conceptual proof of that result as well that relies on the triviality of modular forms. So there are, I mean, I think it's a general principle, and usually when you prove something on the basis that there are no modular forms, it's usually something kind of deep. I mean, it's sort of yeah. I mean, and then of course, I mean, in all these four themes, they're all kind of the starting points for many other questions that one could develop. None of these areas is actually, even the classical thing growing out of Lagrange's theorem is very much a lively subject today. There are still many open questions that are being studied and explored, which are sort of far-reaching generalizations of the modularity of the theta series, which I alluded to in the earlier slide. But that would be another lecture.
Are there other questions? You can use that one, yeah.
Can you prove the Legendre 3-square theorem using this modular approach?
Oh, you say the 3-squared theorem?
Uh-huh.
Yes. So if you look at sums of 3 squares rather than 4 squares, of course the theorem then is a bit more involved, because not every integer is a sum of 3 squares. 7 is not, for example. But there's a characterization of the integers that are sums of 3 squares. And then the natural January series you write down is a modular form of weight 3/2, right? Because I told you that when you have a quadratic form with k variables, you get something of weight k over 2. So in this case, you get something of weight 3/2. So the exponent that appears in the automorphy factor is not an integer, but the half of an integer. And that leads to further subtleties and so, but indeed one can write down this generating series, analyze it, and see that it's some kind of theta series, and thereby conclude, get strong information, including closed formula for the number of ways. But that involves more subtle arithmetic functions, like class numbers, rather than just the divisor function. But it is indeed a very interesting, yeah.
Just comment that monstrous moonshine also depends upon the vanishing of a lot of spaces of way too much.
Absolutely, yeah.
The algebra is integrality of coefficients of the J function.
Yes.
As well.
Yeah, I mean, when you go to lectures on moonshine, you're always hearing about genus 0, right? Genus 0 properties, yeah.
Other questions? I have a question.
Okay.
Can you go back to your theorem, the last one from before?
Okay, this one, yes.
These algebraic numbers, AP, are they explicit?
They're completely explicit, yeah. So of course I pushed under the rug here. I didn't say at all how we got this theorem. We sort of followed so the idea of Gros-Zagier was to look at generalizations of modular functions in two variables, the so-called Hilbert modular forms, and look also at natural non-holomorphic families of such modular forms. They write down some Hilbert modular Eisenstein series depending on a complex parameter S. And in their context, this family vanishes. Therefore, it's natural to take its derivative. And when you do that, you get a non-holomorphic modular function that's invariant under SL2Z, but then there's a holomorphic projection. And so when you follow this complicated sequence of operations, at the end of the day, you get a classical modular form of the weight and level. In other words, you get the zero function. And so you're going through a huge effort to write down these horrible expansion of Fourier coefficients. But the great thing is that when you stare at these coefficients, you see coming out j of tau 1, tau 2, j of tau 1 minus j of tau 2 minus a finite linear combination of logarithms of algebraic numbers. So that's what's really the idea of Gros-Zagier. So here we do something very similar. We take some theta series, but Hilbert modular theta series, put them in p-adic families, because our thing is p-adic, and take the derivative relative to some weight variable, take the diagonal restriction, take something which plays the role of the holomorphic projection, which is the ordinary projection, and just carefully write down at each stage what the Fourier coefficients look like. And at the end, we're left with this expression here, but then this AP is a completely explicit quantity.
Thank you.
I also have a question. The JP of tau 1, comma tau 2 plays a prominent role. Is there a JP of tau?
The JP of tau, yes, there is, but it's a funny thing. Like, so the J function, what characterizes it, so you could ask, for example, I mean, you know very well, but why is there 744, right? And it's because we sort of chose to normalize the function so that it has a 0 at a particular CM point, like 1 plus root minus 3 over 2. And so you kind of pin down the J function by its divisor. So you can do something similar here. There's a notion of rigid meromorphic cocycle, which is a sort of an object that has a divisor concentrated at real quadratic irrationalities. And when you're looking at real quadratic fields, the natural smallest element is the golden ratio. That's the real quadratic field of smallest discriminant, namely 5. And so you can write down a rigid meromorphic cocycle whose divisor is concentrated on the translates of the golden ratio. And that's a sort of a natural candidate for J. And then the values of that thing are going to be related to, yeah, we're going to generate class fields. And because Q squared 5 is class number 1, et cetera, it's sort of defined over Q, whatever that means.
So I guess what sort of following up on that, you can think of J as J of tau minus J of 0, and sort of similarly, then you can think of the JP as like as JP of tau being JP of tau minus JP of whatever corresponds to golden ratio. That's sort of what you're saying?
No, so that's too simple.
Oh, not minus, but J.
Yeah, I mean, so there's a strong analogy between this. So the objects that are lurking in the background, which I didn't talk about at all, are not modular functions. So we ask ourselves, what plays the role of modular functions? And the object that we relate to are what we call rigid meromorphic cocycles, which are classes in the first cohomology of a p-arithmetic group with values in the multiplicative group of a space of meromorphic functions on the p-adic upper half plane. So it's a bit of a complicated thing. The theory is very much a multiplicative one. So the nice thing about modular forms is that they have both an additive and a multiplicative structure. And that's very useful for proving various things. It's useful in Gauss's solution to the class number 1 problem, all kinds of applications. Our theory is only a multiplicative one. So these things do not behave in any simple way when you try to consider their differences. And I think it's one of the origins why, I mean, I should really emphasize that in spite of the algebraicity result, this theory is far less well understood, and there are many, many things that we don't understand about it. And that's one of the sources of the difficulties, yeah.
Are there any more questions? If not, then let's thank Henri again.